Hi everyone, this is André. In this video I'd like to show you a thing or two about FOIL analysis, questions that have been asked, project files which have been submitted and on which, in which there are some issues. And as we go along I'll show you a few tips and tricks on the way I use XFLR5. So let's consider this project file, for instance. This is a mesh of type 1 polars in view of a plane analysis. And there are 2 or 3 things which need to be improved or even corrected on this mesh of type 1 polars. So to illustrate, I'll zoom in the first graph here by typing 1 on my keyboard. And the first thing to notice is that we have some high density of polars at high Reynolds value, whereas the viscous behavior in fact doesn't change that much. And what I wanted to point out is that this is really unnecessary. It is important to have some density of polars in the low Reynolds numbers, and this is quite okay. But in the high numbers, it's just unnecessary, and it means that the FOIL analysis will take longer than is necessary. What I do typically is I use a sort of a geometric progression in the Reynolds numbers, and you can see this if you launch a batch analysis, edit the list of Reynolds number. Well, this is not quite a geometric progression, but it gives you an idea. Okay, more importantly, if we look at the legend here, we can see that in fact we have 2 types of polars which have been defined. One with 0 Mach number and one with 0.15 Mach number. And the 2 sets of polars are mixed together. Now this can be an issue when we run the plane analysis, and why is that? Well, the plane analysis will use the Reynolds number to deduce viscous results from this mesh of polars, and it will use the Reynolds number as a key. And using this key, it will find in fact 2 polars instead of 1, and it will use one of them, those 2, but you won't know which. Therefore, the viscous results will be defined using randomly one polar or the other, one which has been defined at Mach 0 or the other which has been defined at Mach 0.15. So the important thing here is that for each Reynolds number to have only one type 1 polar. The Mach number can be different from polar to polar, so can the transition criteria be different, but the important thing is that we should have only one type 1 polar for each Reynolds number and not 2 or more. Okay, next thing I like to comment on are these strange points here, which appear sometimes in the polar graphs. Let me display all the graphs by typing A on my keyboard, and I'll reset this top left graph by moving the mouse in the graph and typing R on the keyboard. On this 4th graph, I've plotted the drag coefficient versus the angle of attack, and we can see that at low angles of attack we have low drag, which translate to very high glide ratios. Now this is just unrealistic. Obviously there was a calculation issue here, and this needs to be corrected. So to show how this should be corrected, I'll use another FOIL which I know produces the same kind of behavior. I'll hide all these polars and define a NACA foil 1410 I'll type OK. Now a trick here, a tip here, when you get a dialog box like this one, but it works also for almost all the others, if you type enter once, it will move the focus to the OK button. I've just typed enter on my keyboard. And if you type enter a second time, it will accept the dialog box. And we've got the NAC F1410, which has appeared in the top list box here. Let's switch back to the polar view by typing F8 on the keyboard. Now, same, I'll define an analysis by typing F6. 100,000 is quite okay. I'll type enter once to move the focus to the OK button, and OK a second time to accept the analysis, which has now appeared in the top list box. A quick thing here, if I type again enter, the focus has moved to the analyze button here, and if I type enter a second time, it just runs the analysis. Okay, let's reset this polar for the time being, and I'll run this analysis again with special values which I know create the issue which I've just shown. Okay, analyze, close. There we are. I'll thicken this this polar so that you can see it. Darken it a bit. Okay, and you see that we have the same issues here at low AOA, some very funny points which have been created. Now I realized that I did not check the store operating point checkbox, so I'll do this again. Okay, and let's see what they look like, what these operating points look like. Now, I know that they correspond to AOAs between -4 and -6, but assume we didn't have this graph here, and I wanted to know which AOAs are these points. What I can do is use this option here, highlight the current operating point, and this creates a highlighted point on all the graphs. -6.2 is this point, at the upper range, 6.5 is this one. So I'd like to identify this one at almost zero drag, so -4, -3.7, okay. Now that it is selected, let's switch to the operating point view by typing F5, sorry, or clicking here. I'll thicken a bit the foil, align. Okay, and let's display the boundary layer, which here again I'll change its style so it appears better, so you can see it. Let's thicken it a bit. Okay, and what we can see is that we have a sort of a divergent boundary layer calculated by Xfoil. Now I don't know why this happens, I have no explanation for it, but what I know is that this should be corrected, and the way to do this is to switch back to the polar view and run the analysis with other values. So I'll reset the polar and run it from -7, let's say, to 10 by increments of 0.5, 0.25, maybe that will be a bit better, and let's do that. By the way, another tip here, last time we ran the analysis it went from -7 to +6, so the last converged value, or +6 point something, yeah, the last converged value of Xfoil was for 6 degrees. Since we're starting from a very different value here, which is -7, we should, to facilitate the analysis and the convergence, initialize reinitialize the boundary layer to default values. You should do this each time a calculation is by Xfoil is for a configuration, airfoil or AOA, very different from the previous one. Okay, and for these values, the abnormal behavior doesn't occur, so that means we've corrected the problem. Okay, and I think one last thing I wanted to show you. There have been some issues in the multi-threaded batch analysis. I think most of the issues have been corrected by now. There still can be some problems if this checkbox update polar view is activated. Let's run this analysis starting from 0, and I've activated the view, so the view updates in the background live, and that's quite pleasant to see. The problem arises when you have a high number of polars to calculate, and if you request the update of the polar view in the background, this will overload the display engine and slow down tremendously the analysis. And in some cases, it seems that the display in the background can just not follow the rhythm of the analysis, and it can lead to a crash. So if you have a low number of polars to calculate, you can activate the checkbox. If you get some increasing numbers, perhaps 100, thousands, then I strongly recommend that you uncheck this checkbox here. Okay, and I think that's all I wanted to mention today. So thanks for watching, and watch out for the next videos.